So we are trying to discuss this adjacency matrix. The next matrix is. So adjacency matrix is also a binary matrix of a graph G. Let's say a graph G with n vertices and no parallel edges. Okay, and no parallel edges. Is and the adjacency matrix of this graph G is an n by n matrix. N by n symmetric matrix, symmetric binary matrix. And let's say this is X matrix, where this Xij, so it is a square matrix, n by n matrix, it is a square matrix, not rectangular. Incident matrix was a rectangular matrix. Here it is n by n, where n is a number of vertices in a graph G. Is defined as Xij is equal to 1 if there is an edge between ith and jth vertices. So if there is an edge between ith and jth vertices, then that entry is 1, otherwise it will be 0. If there is no edge between them, okay, so this is the definition, or I can say a matrix, adjacency matrix is there. And the adjacency matrix is generally denoted by X of G. This is a notation for adjacency matrix. For example, if you have been able to plot the adjacency matrix of some graph, so let's say the adjacency matrix of the graph this. Suppose this is the matrix, this is the graph you have. Let's say this is the graph G, where you have this is V1, V2, V3, V4, V5 and V6. There are 6 number of vertices, and the edges will be E1, E2, E3, E4, E5, this is E6, E7 and E8. 8 edges is there. Now we'll need to write down what is this X of G from this graph. So X of G, if I want to write down, then this is how many number of Vertices are there 6. So it is a 6 by 6 matrix. This matrix is a 6 by 6 matrix. Okay, so you will have this matrix is 6 by 6. I just write down 1, 2, 3, 4, 5, and 6 here. Now, so there is no parallel edges and self loop is there. So that's why for V1, so this is V1, 1, 2, 3 represent the vertices. So 1 to 1, there is no edge is there, so that's why it is 0. 1 to 2. So there is an edge between vertex 1 and vertex 2. So that's why we can put 1 here. 1 to 3, there is no edge between 1 to 3. 1 and 3 are not connected by an edge, so that's why 0. 1, 4. Sorry, 4 this is 4. 1, 4 is also not connected, so that's why it is 0. 1, 5 is connected by an edge, so that's why it is 1. 1, 6 is connected by an edge, so that's why it is 1. 2, 1, so it is a symmetric matrix. So whatever the quantity in the first row, that the same quantity will come into the column also. So the same quantity you will have here. Now 2 to 2, it is 0 because there is no loop. 2 to 3, if you want 2 to 3, there is no edge between 2 to 3. 2 to 4, there is an edge. 2 to 5, there is an edge. 2 to 6 is no edge. So this should be copied. 1, 0, 0, 1, 1, 0. Here it is also 0. 3 to 4. 3 to 4, there is an edge. Then other will not be edge. This is 1, 0, 0. Here it is also 0, 4th. 4 to 5 is edge and 4 to 6 is also edge. So this is copy here. 5 to 5, 0. 5 to 6. 5 to 6, no edge. That's why here you also have 0 and 6 to 6 is also 0. So finally, this is the graph. From the graph we can have, this is the metric. Okay, so this is connected graph. In the connected graph, you have such metric. What will happen if the graph is disconnected? Can you tell me what will happen if the graph is disconnected? So that means, for example, this is the graph you consider. This is whole graph G. So if I can say this is V1, V2, V3, V4, V5, V6. If I can plot what is X of G, that means there is 1, 2, 3, 4, 5, 6. 6 edges are there. So that's why this matrix is of this type. 1 to 2 and 1 to 3. That is. So I just have, and all rest of them is 0. Then this should be copied. Here it is. 1 to 3 is also, I should write. Here 0 and here 1, 1. So this is the matrix. Then for 2, this will be 0, this is 1. Here it is 1, this is 0, and all this entries will be 0. So here also you have 0. Now for 4, you will have, here it is 0, here 1, 1. So you have 1, 1 here. For 5 only 4 is there, other entries 0. For 6 only 4 is there, so this 2 entries. So what is this matrix? This matrix is actually a component matrix that you can see. You just see that this is a 0 matrix. Here is also you have a 0 matrix. This 2 component you will have. Why you will have a component? Because there is 2 component in the graph. So if you have a larger component in the graph, then you can partition your matrix into that manner. So in general, if the graph is just disconnected and has 2 component, let's say G1 and G2 are the 2 components. If and only if the adjacency matrix X of G can be partitioned as X of G is equal to X of small g1 0. This is a 0 matrix. X of g1 is a 1 matrix, as I told you that this is my X of g1 for this, and this is X of g2. This is g1 and this is g2. This G is partitioned into 2 parts. It has 2 components. So that is the way you can represent here 0 X of G2. Okay, where this X of G1 is the adjacency matrix of the component G1. And X of G2 is the adjacency matrix of the component G2. So these are the 2 things we can have. In fact, there is one result which is very important results. Using this result, you can establish whether your graph is connected or not. Okay, so let G be a graph with n vertices. Let us say that vertices are v1, v2 up to vn. And let X be the adjacency matrix of G. So X, capital X is the adjacency matrix of G. Let Y, I'm defining as Yij, which is also n cross n matrix, be the matrix such that, and this Y matrix is actually a sum of powers of X, that is X plus X square plus X cube up to X raised to n minus 1. Okay, then G is connected So if you want to say that G is connected, if and only every entry in this Y, every entry ij we have Yij is not equal to 0. That means Y is or Y has no zero entry of the main diagonal. Then you can say that the graph G is connected. So, okay. So if you have the sub adjacency matrix and using the adjacency matrix, you can say whether the given graph is connected or not. Let's say some example. So I am taking this example. Check whether the graph G having following adjacency matrix. X is connected or not. You have to tell me whether the X which I have written here, which is the adjacency matrix of some graph G, it is this 0 1 1 1 1 0 1 0 0 0 1 0. One more row is there. Sorry, one more column is there. So it has to be one more row is also there. So this is the third row is written. Fourth 1 0 1 0. One and 1 0. Okay, so this is the matrix you have. Now we have to find out whether the graph made of this matrix is connected or not. So as per this argument, you have to check this Y, that is x plus x square plus x cube up to so on, will be connected or not. So if this is my x is this, what is the x square? You know how to do the matrix multiplication. Might be you have learned in your linear algebra course in previous semester. Should I write directly what will be the x square? Everyone know how to calculate the x square. No one is answering. Does everyone know how to calculate the matrix square? You have not learned in your linear algebra course?
Yes, sir.
You have learned? Yeah. So this is not time to teach you how the matrix multiplication is done. You should know that because you did your linear algebra course. Okay. So when you do the matrix multiplication, that means you have to multiply this row to this column, and that will gives me 5. First entry is 5. Then this row to the second column. To multiply this row, the first row to the second column, then the entry is 1. Then the first row with the third column, then entry will be 2. You check. This one, the things you can get. Next one you will have 1, 2, 1, 2, 1, 2. Here is one more. 2 is there. 2, 1. 1, 2, 1, 2, 1, 1. Then 2, 1, 3, 1, 2, 1. Then 2, 2, 1, 3, 1, 2. The next is 2, 1, 2, 1, 3, 1. And 1, 1, 1, 2, 1, 2. So this is my x square if I compute from this x. What is the target or what is our objective is to check whether this y having any non-zero entry or not. So according to this y, what is the y we have? It is x plus x square plus x cube plus x raised to 4 plus x raised to 5 because there are 6. So according to this, it will be x power n minus 1. You have to go until n minus 1 power. So you have to go until x raised to 5. Should I need to calculate this entries? I have calculated x
No,
square.
sir.
X square contains all the, you can just see that it is all the entries are non-zero. All of main diagonal entries are non-zero. Here, of main diagonal entries are non-zero. And when you multiply this x square to x, again, all of the entries are positive entries, either 0 or it is positive. Okay, so this x cube having the positive entry, x raised to 4 is also having the positive, no one is having the negative entry. So if the sum of this two, first two, is non-zero, so sum all of them, if you do the sum of all this, that is also contains a non-zero. So what should I write here? Since x square has all diagonal entry, sorry, all of diagonal entry, non-zero, y also have all of diagonal entry non-zero. And that gives that, and hence according to the previous result, this G is connected. So without plotting a graph, you can plot them, and if you want you can just verify also. You just try to plot what is this graph is and find out whether that graph is connected or not. I'm giving you two examples to work out with yourself. Check whether the graph G having following adjacency matrices is connected or not. No need to plot them. Without plotting, you should conclude whether it is connected or not. So for that, what I told you, you have to calculate this y. If the off diagonal entries of this y, off diagonal means diagonal except diagonal, all of them entries should be non-zero. If it is there, then you are true. So I'm giving you first example here. Consider this 0 0 1 0 0 triple 0 1 0 1 0 0 0 1 0 1 0 0 1 and 0 0 1 1 0. This is the first graph or adjacency metric of the graph. The another one is this 0 1 0 0 0 1 0 0 0 0 0 0 0 1 0 0 0 1 0 0 0 1 0 0 0. So this is another graph. Okay, check whether these two graphs are connected or not. So you know now what to do. If this is x, you have to calculate y. In this, it is x plus x square plus x cube plus x raised to 4, because there are 5 number of vertices. So you have to reach up to x raised to 4, and here in this y you have to check whether you have a non-zero entry is there or not. If any of the entry is 0, then you cannot tell that the given matrix or given graph is connected or not. So this is about the adjacency matrix. Then there are other different types of matrix are there. The one of them is a circuit matrix, fundamental circuit matrix. All sort of things we are not discussing here. We'll go to the next one. This is called a planar graph. So the next topic is a planar graph. To understand a planar graph, first of all, you should know what you mean by plane graph. A graph, it's called a plane graph. It can be drawn on a plane in such a way that any two of its edges neither meet only at their end vertices, or they do not meet at all. So if you can able to draw a graph in such a way that any two edges is either they will never meet or they will meet at their end vertices. This is only the things is there. So I'll write that. What I'm talking is a graph. It's called a plane graph if it can be drawn on a plane in such a way that any two of its edges either they are meet only at their end vertices, or they do not meet. So, what is the definition of a planar graph? A graph which is isomorphic to a plane graph. That graph it's called planar graph. So the definition is a graph which is isomorphic to plane graph. It's called planar graph. For example, I'll give you an example. If I consider this graph, this is graph G1. Can we plot this graph G1? So what will happen here? This vertices, that is the vertex, this one, so this edge and this edge, they are meet at here. But what is what I have told you a definition of the plane graph is their edges, they are meet at their end point or end vertices, otherwise they will not meet. So so this graph G1 is not a plane graph because their edges are meet here, but this is not a vertex. But this G1 is a planar graph. Why? Because we can able to draw this graph in such a manner that so we can able to draw this graph. So this graph and this graphs are isomorphic graph. This G2 graph is isomorphic to G1. And G2 is a plane graph. So that's why G1 is a planar graph. It is not a plane graph, it is a planar graph. Yes. We'll give you another example also. So let's say this. Here there is a two vertices. And this is also joined. So I'll say this is G3. Can you say this G3 is a planar graph? It is not plane graph because their vertices are intersecting here and here and here. Okay, so this is not a plane graph, but we can able to draw that as a plane graph. So if you have this 5 vertices already there, we'll plot that one first. And this 2. And then we'll plot this. In this manner. This is G4. So this is a plane graph. And this is a planar graph. It is not plane graph. Now it is interesting fact that some of the graphs are plane graph and some of them are not plane graph. The graph which is not planar graph, it is called non-planar graph. The graph which is not planar graph, it is called non-planar graph. Can you able to draw a non-planar graph? So there are many non-planar graphs are there. Okay. Let me draw this, one of them. So if I plot the graph in this manner, then this graph is never can be drawn as a plane graph. So this is an example of a non-planar graph. So how to decide whether the given graph is a planar graph or non-planar graph? So is there any formula for that, so that we can say that the graph is planar graph or non-planar graph? So there are lots of results is already exist in the literature, which tells you that it is a planar graph and non-planar graph is there. So for that, you should understand what you mean by embedding. Embedding. A drawing of geometrical representation of a graph on which the surface is called the embedding, such that no edges intersect each other. And therefore, to declare a graph as a non-planar graph, we must see out of all possible geometrical representation of a graph G, none of them can be embedded on a graph on a plane. So a graph is said to be a planar graph. We know that there exists an isomorphic graph G, which is such that it is embedded on the plane. Otherwise, the graph is non-planar. This is another way to looking at the things. Now I am not writing everything due to the short of time. So what I am saying is a drawing on a geometrical representation of a graph on any surface, it's called the embedding. So we need to embed that onto something. So if you want to say that the graph is said to be a planar graph, if there is a graph which is isomorphic to graph G, such that is embedded on the plane. Embedding on a planar graph on a plane, it's called the plane representation of the graph G. So in this graph, for example, we'll talk about now in this graph, there are region and faces are there. A plane represents a graph divides the plane into the region or faces. For example, this is whole graph is there. This is a plane graph we have plotted. So how many region is it to divide? So the first one is this, second one is this. So this is divide the first region, this is a second region, this is the third region, and the fourth one is outside region. So that is a definition of the region or faces. For example, in this graph, so how many region this whole graph is divided into? So 1, 2, 3, 4, 5 and 6. So this will divide into 6 region and so on. And there is very interesting formula is there, which says that a connected plane graph with n vertices. This formula is known as Euler formula. Euler's formula. A connected plane graph, planar graph, G with n vertices and e number of edges has how many faces? They has e minus n plus 2 number of faces. For example, faces or region, I can say. Both the word is used. For example, in this previously we have plot. So this has 4 region. So if I want to calculate, so it is always satisfies this formula, that is f equal to e minus n plus 2 is always satisfied. For example, it is f is 4. So this side is has to be 4. Number of edges will be 1, 2, 3, 4, 5, 6. So e is 6, n is 4 plus 2. You just see that the answer will be 4. In this, you can check f is 6 here and n minus e plus 2. Number of edges will be 1, 2, it was e minus n plus 2. So the number of edges are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 edges are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So E is 11. Number of vertices are 1, 2, 3, 4, 5, 6, 7. Minus 7 will be gives you 5, 4. 4 plus 2, 6. So it will have, so it will always, this any planar graph, for that this will always satisfy. Here they have talked about the K5 and K33. The complete graph K5 and complete bipartite graph K33 are called Kuratowski's graph. Kuratowski's graph, K5 and K3. And the Kuratowski was a Polish mathematician. And he has proved that this K5 and K33 are non-coplanar graph. See, this is very interesting research topic is also. Given a graph which is a planar graph or non-planar graph, it is, people have written a lots of research paper on it. And by proving it, the given graph is planar or non-planar, that is, one can do some of the very important. So it is these two graphs, that is K5 and K3, 3 are a non-planar graph that was established by this Polish mathematician. And that's it for today. I think so. I should stop, and with this, we'll finish this portion of a graph theory also. Okay, so nothing to say into the graph theory now.